Okay, so hello and welcome to our last topic, really, of the course, which is the fundamental theorem of calculus and what we call the net change theorem. This is one kind of facet of what we call the fundamental theorem of calculus that we're bringing into this course. This is the bridge to Calc 2, and it's kind of the culmination of Calc 1 and leads us to this place where um, Calculus 2, which focuses on integration, kind of takes the reins and goes from there. So today we're hoping to understand the statement of the fundamental theorem of calculus in this context of the net change from what we've studied so far with the area and distance problem, the definition of the definite integral, and what this all means, um, and how it connects to our current understanding, how to apply this to calculate net changes and solve problems involving this. Okay, so this is kind of our main goal for today. And I'll be unpacking the notation. I'll do a brief example, and then we'll have some more worked examples provided for you in the notes. All right, so let's jump right into it. Um, the fundamental theorem of calculus, what it says is that if you have some function where f prime of t is equal to little f of t. Okay, so we have some other function, like you can think of this as, like your position function s of t, where s prime was equal to v of t. All right, so little f is like the velocity and big F is like the position. Then the total change of f over the interval from a to b is given by the integral from a to b of f of t dt. This is given to the total change of big F, meaning big F of B minus big F of A. So the starting value of F and the ending value of big F over that interval. So again, what this does is gives us a way to calculate the total change in a function given the integral of its derivative. Okay, so what this is doing is connecting this potential value function with its derivative by way of the integral. All right, without taking limits of Riemann sums. So what this says here is this still carries its multiple meanings. It's physical. We can think about it in terms of velocity and um, position and acceleration and velocity, and also geometrical, meaning the idea of signed area. This is in velocity, position, but also any contextual or problem situation, real world. Doesn't just have to be physics. This can be economics or biology, chemistry, computer science, etc. Okay, so what this is doing is connecting the integral and the derivative. Okay, so that is how it's tied to the fundamental theorem of calculus, and we do so through the lens of net change. Now, I'm going to give us an application, and then I'm going to unpack the notation a little bit more because I feel like this will help us do that. So the fundamental theorem of calculus allows us to calculate total change if we know the rate of change. Okay, so as long as we have the derivative function, we can get the total change. For example, suppose a car's velocity is v equals 3t squared meters per second, the rate of change of its position, from 0 to 2 seconds. Then if s of t is the position function in meters, then we know that s prime is v of t. So then the net change in position from t equals 0 to t equals 2 is the integral from 0 to 2 of v of t. And the accumulation of that rate of change is equal to the end position minus the starting position. Okay, so this is how we connect these two things. So let me unpack this example a little bit more. I'm going to scoot down here and then I'll read number 4. Okay, so the problem we were given was, the total change in position, s of t, from t equals 0 to t equals 2 is given by the integral from 0 to 2 of v of t dt And what the fundamental theorem of calculus tells us is that this is equal to s of 2 minus s of 0. All right, and we know that v of t, we said, was given by 3t squared dt. Okay, now we can just go ahead and calculate this using our calculator, all right, and get an idea of what that should be. And we'll do that. So let's go ahead and do that. And so we see it's a grand total of 8. So we know that 8 equals s of 2 minus s of 0. Okay. Now, a few comments here. We got to think about what the units of this are. This is the total change in distance. This would be 8 meters, right? And so 8 meters is the net distance, net change in position from s of 0 to s of 2. Now, we don't know what s of 0 or s of 2 are, right? We were not given this information. No, we weren't. So now, if we knew that s of 0 equaled 0, then we know s of 2 must be 8 meters. That's at the 8 meter mark. If we knew that s of 0 was, let's say, 12, then we know s of 2 must be 20 meters because we know the difference between the two has to be 8 meters from start and stop, etc. Okay, so this is what this tells us. It gives us the net change. And if you wanted to solve a problem that asked you about either one of these values, you'd need to know one of them, because otherwise you have too many unknowns. Okay, so you'd need to know either the starting value or the ending value of this function. So while we're on the topic of units, I do want to kind of talk about that for a moment. So looking at the integral of v of t dt from a to b, let's think of this very informally. From t equals a to t equals b, the units inside this function of what we're accumulating, we talked about this in the area and distance problems. This is meters per second for v of t, and then dt carries the units of seconds. And so if this big S really means sum, and this is start and stop, I'm taking the sum of these products. Well, all the units of these products are going to have those seconds canceled, and you should be left with something number of meters. Okay, so this is very important because we don't just limit ourselves to physics problems. This could also be, a rate of flow. This could be a density, right? Like kilograms per meters cubed times, meters, something like this. If we're going along a thin line through a solid, this could be, whatever it might be. If your r of t dt, let's use a different variable. You take the r of x dx. These will each carry their own units, and so um, the end result will carry those units of r of x times the units of the input x. This will always be the case. And so if they simplify, great. They might not always simplify, right? Like if this is kilograms and this is meters, well, then you're going to just be left with kilogram meters, right? So that's an important idea, that since you're adding up products, you will need to have those units resolve on the right-hand side. All right, and the last thing I wanted to say about this particular example is that, I'm going to move to a new page here, which is that the integral of 3t squared dt from 0 to 2 give us s of 2 minus s of 0. Now, we don't know what the position function is. However, we do know that that s prime of t is equal to v of t, right? V of t is the derivative of s, and we know that that value is 3t squared. Well, just based on what you remember, not using any techniques of antidifferentiation, because we don't really do that in this course so much, what might s of t be? Well, if this kind of looks like it would have been a power function, because it must have for sure, so it might have been the power that comes before this, which would have been t cubed, right? Would this fit? Well, s prime of t would be 3t squared, so that does fit. The problem with integration is that that would work for that plus any constant I had over here. If I had t cubed plus 100, that would also be the case. If I had t cubed, minus 174, that would also be the case, right? Because that constant would drop off. So there's actually infinitely many possible s of t's. But since this difference is happening here, that balances itself out. So we can really just take this as our candidate for now and say t cubed is a good candidate for s of t. And we can say, well, this would be then, instead of s of 2, would say 2 cubed minus 0 cubed. And what are we left with? Our exact value of 8. Okay, so here again is more information that the fundamental theorem of calculus ties together the derivative and its the function and its derivative, right? And the net change of that potential function, whether it be position or whatever. And that's all this last paragraph states, is that there is a deep connection here. It's not immediately straightforward that this should be the case, but hopefully from our kind of trajectory in this chapter, following the area and distance problem as our motivation, coming up with a way to approximate that distance traveled by using boxes and seeing that making them smaller and smaller is a better way to go, and that the limit of that must be this exact signed area, and now seeing that that generally applies to the net change of a function over an interval. We can accumulate its rate of change. And now you're seeing how the units will agree with this, and you're seeing how the idea of maybe an antiderivative would agree with this. Okay, and so we'll have a nice handful of problems that will push you to kind of understand this in a more applied way. But this is our final idea of the course, and so I won't pepper you with too much more here. I hope that the depth of this comes out through the examples and our discussion around it. But you've made it, okay? No more new stuff, I promise. And I hope you're able to study up and review everything we've covered well before the final exam. And as always, get in touch with any questions you have. But here again, this isn't quite the fundamental theorem of calculus as you'll see it elsewhere. This is one kind of lens into it called the net change theorem that I think we're getting most bang for our buck before jumping the bridge for those of us going on to Calc 2. All right. So hope you enjoyed. We'll see you in the discussion. Have fun.